All right, welcome. So last day we talked about different probability rules. It was probably a review, right, for hopefully all of you. But it's good to have kind of the basics down again. So we covered the review or kind of the basics, and then today we'll start by talking about conditional probabilities. But before I do that, I was thinking for Friday, because we have our little Friday class, instead of making you show up for that Friday class, because I don't think I'll be able to finish all of chapter 4 today, but what I can do is I can, what I was thinking of doing was if I could just record the remainder of chapter 4, and then you can watch it on your own time. And so for Friday, because remember, there's no class on Monday, right? So it's a long weekend. So I just want to kind of give you some freedom, I guess, because that's nice. And that way you don't feel like you're skipping out on anything, right? You can do it on your own time. So for Friday, I will post a video of the remainder of chapter 4, right? So depending on how far we get today, we'll see. So of the remainder of chapter 4, and you can watch it whenever it's convenient for you. Okay, good. I'll also make a note that we don't have class on Monday, right? No class on Monday because it's Thanksgiving. Okay. So just as a heads up, so that's why so this means also no scheduled lecture for Friday. Okay. So we can all kind of use a break, I know. So I think that'll be good. If you absolutely hate that idea, let me know, and I'll try to help you out. Okay, so I won't do a review because it was kind of review of review. Hey, fun. I see a thumbs up. Nice. All right. So last day was kind of a review of some concepts that we already knew. So we kind of last day we reviewed basic probability theory, probability, maybe I should call them probability rules. Okay. So today, that's not really a review, but starting fresh today, I want to start talking about conditional probabilities. What can be hard with this stuff is I know sometimes I feel like, oh, why do I need to learn all this theory? It doesn't matter. Why would I care about all this theory? It's not about the theory so much. I don't expect you to memorize the theory, but we do need to be able to apply the theory and be aware of just kind of how to think about things. For example, conditional probabilities. If you are working at a bank, like we'll see in the example, right, then you need to be able to figure out probabilities of someone not paying their bills on time, right? If you work at ICBC, for example, so an insurance firm, then you need to be able to figure out the probability of someone getting into an accident, right? What's the probability of that happening? Because then you'd have to pay for the damage, right? And so we use these probabilities, and conditional probabilities are, of course, part of that. So let's first remember what conditional probability is. Okay. And then I do have an example, because I find that conditional probabilities are pretty tricky. And so it helps to go through an example, and then we can kind of see it happen. And that'll be good. Usually we end up using a tree diagram, right, for conditional probabilities, for other probabilities as well, but definitely for conditional probabilities. So a conditional probability is when the probability of one event depends on whether another event has already happened or not. Okay, for example, if you know that your sibling has some inheritable disease, then you're more likely to, the probability that you have that is higher, right? By knowing that your sibling has it, or maybe that your mom has it, or your dad has it, right? Knowing that it's in your family increases the probability that you would have it, right? And so even if you think about COVID, right? If you know that you were around someone who had COVID, then the probability that you have COVID is higher now, right? And so we use conditional probabilities every day, and we understand what they are. It's just when we introduce the notation that it gets a little bit difficult, right? And so I want to just try to break that down and show you what's going on today. So, okay. So just to introduce it here, what if we have an event A with probability P of A? Okay. If we learn that a related event, which we denote by B, has already occurred, then we can take advantage of that information, and we can calculate a new probability for event A, right? That's if A depends on B, okay? And so that's where we get our conditional probability. And so it says it here, but the probability of A given B is written like this. And that vertical bar, right, that straight vertical bar, you read it as given, right? So what this says is the probability that, or the probability of A, if we know B has happened. Okay. So if B influences A in any way, then we say that they're dependent, or that it's a conditional relationship. Yeah, so let's have a look at this example here. I did cut out the data summary, and you know what? Maybe I'll do this. So consider a bank that's interested in the mortgage default risk for its home mortgage customers. So I didn't include table 4.3, but it just shows the first 25 records of 300 home mortgage customers at this bank. And so it's just the data, like chopped up data set. And so we're talking about Lancaster Savings and Loans. So if you see Lancaster later, it's just the bank that we're talking about, a company that specializes in high-risk subprime lending. Some of these home mortgage customers have defaulted on their mortgages, and others have continued to make on-time payments. Of course, that's going to be a variable of interest, right? A variable because we don't know if a certain customer is going to default or not, right? That it varies from customer to customer. And so that's going to be our main variable. These data include the age of the customer at the time of the mortgage origination, the marital status of the customer. We assume that we can only be single or married, nothing in between. Okay. The annual income of the customer and the mortgage amount, the number of payments made by the customer per year on the mortgage, and the total amount paid by the customer over the lifetime of the mortgage, and whether or not the customer defaulted on her or his mortgage. For this question, we're going to focus on 2 of these variables, but there's lots of information here that we could use and that we could incorporate into our analyses, right? This is just one of the questions that we want to answer. And that question is going to be whether the marital status, right, is conditional, or rather the other way around. The marital status isn't affected by whether they default on their loan or not. No, that's not how it works, right? But the other way around, whether we default on our loan or not might depend on our marital status, whether we're single or we're married. Okay, and so that's what we're going to look at. Okay. We will focus on the marital status assume single or married are the only categories, are the only possible categories. Okay, so we will focus on the marital status. And of course, I'm just stating that assumption. That's not necessarily true, but in this case, that's what we're assuming. And its relationship to whether a customer defaults on a loan or not. Okay. So I'm going to bring these in instead of side by side, blow them up a bit. And I'll bring in that cross tabulation as well. So Lancaster Savings and Loan is interested whether the probability of a customer defaulting on a mortgage differs by marital status, right? So we're going to define some of our variables. S is going to be that the customer is single. M is going to be that they're married. You could have used the complement of S here, right? Because it's either one or the other. But for emphasis, we're going to use M. Okay. Could have used the complement of S, or vice versa, right? Married or not married. Okay. D is the event that the customer defaulted on his or her mortgage, and then the complement of D is that they didn't. Okay. And so here we have the cross tabulation. So we took the data and we created this cross tab, And we have the marital status here, which is either married or single and nothing in between. And then we have the no default versus the default category, right? And so we've got these totals in the margins, and we are looking at a total data set of 300 customers, okay? So if we're interested in the probability of someone defaulting based on their marital status, what we're showing is whether 79 versus 41 is different. Now, we can't just compare these values because there are different, the probability of someone being married, right, is 143 over 300, whereas the probability of someone being single is 157 out of 300, right? And so we can't just look at the numbers and compare them, right? But we can get an idea for, in the married column, right? If the probability was equal or roughly equal for the no default versus the default category, right? What we could look at is 64 versus 79. Not that big of a difference, right? Slightly higher in the default column. Whereas if we look at the singles, right? So just the group of singles, 116 versus 41, all of a sudden we have this really, really big distinction, right? And so that makes us suspect, right, that something's going on, right? That maybe the default versus no default category depends on marital status. Okay. So here, comparing the D and not D counts in each category, M or S, we suspect that the default, right, whether a customer defaults on their loan is dependent on marital status. We suspect that whether a customer defaults on a loan or not depends on marital status. It would be pretty silly to try to do it the other way around, right? To see if marital status depends on whether someone defaulted, right? Because it doesn't really work that way. Okay, so in this case, right, does your marital status, does that have anything to do with whether you're going to default or not? Same thing as I think it's males under 25 pay way more in car insurance. And that's for the exact same reason, right? Because that specific category, right, or that kind of combination of categories puts you in the highest risk group of having a car accident. And that's just how it is, right, based off of data. So, good. So, if we want to know, right, the probability that a customer defaults on his or her mortgage, given that the customer is married, we could do that calculation without any of the formulas, right? Because what would we do? Okay, so we want to find the probability that a customer defaults on their mortgage, given that the customer is married, right? And so now we restrict our focus to the married column or row, sorry, right? And so we're focusing on these 143 people, and how many of those defaulted? Well, we see that 79 out of 143 defaulted on their loan. So the probability is going to be 79 over 143. So we can go here, and they kind of develop the same thing, right? And so to calculate the probability of D given M, right? The probability of defaulting given that you're in the married column or row rather. First, we note that we're concerned with only the 143 customers who are married, right? And then we know that 79 of those 143 defaulted on their mortgages. So the probability must be 79 over 143, which is 0.5524. Okay. Usually, again, we report in percentages, so 55.24% chance that they default on their loan, assuming that we know that they're married, right? So given that they're married, then that's the probability that they default. Okay. So what's the probability that they default if they're single? Well, we would do the same thing, right? What could we do? So now we're focusing on the single total, which is 157, but now we have 41 out of 157, which gives us 26.11. Okay. So what we can do, and maybe I'll try to bring in a calculator here, because I think it was 47 divided by, now I can't remember. 41 out of 157. I just want to show you what that becomes. 41 out of 157. .2611464968. Okay. And so that's where we get the probability from. Or what we could do is we could map the calculation that we just did kind of intuitively. We can map it back to probabilities. I think the easiest way to show you, though, is just to give you the formula that we end up using, right? Because what are we doing? Sorry, scrolling around here. Catch up. Well, so for 41 out of 157, really what we're looking at is we're looking at single and defaulting divided by the number of single people, right? So we can talk about those as probabilities. You just throw probabilities in front. So 41 out of 300, that's the probability of being single and defaulting. Whereas this 157 is the probability of being single. So what I want to do is I just want to show you how this table breaks down . .64 out of 300 is the probability of M and no default. Okay. .116 out of 300 is the probability of single and no default. .79 out of 300 is the probability of being married and defaulting. .41, let's see here. 41 out of 300. Notice how I'm dividing by 300 all the time, is the probability of being single and defaulting. $143 out of 300 is what? The probability of being married, right? Because it doesn't take into account whether they defaulted or not. It just is asking, are you married or not? 143 people said yes. 157 out of 300 is the probability of being single. $180 out of 300 is the probability of not defaulting. And finally, if I can find some space here, 120 out of 300 is the probability that they do default. Okay. So we could use this table, this crosstab, to find probabilities, or we could find the proportions and then use the probabilities that way, same thing. Or usually we can just intuitively reason our way to the answer, right? If we have the crosstab. So I want to bring in this conditional probability formula. Okay. So the conditional probability, the probability of A given B, and I will say that the second one is pretty redundant because you could just rearrange the letters. It's the same. But the probability of A given B is the probability of A and B, right? And so if we want to know the probability of defaulting given that they're married, well, that would be the probability of defaulting and being married, right, divided by the probability of being married, right? So here, what I find helpful is that this value is the one that goes here, right, in the denominator. Whereas the numerator is really just A and B, right? It's A given B, so it becomes A and B divided by that second value. Notice here, right, A. Okay. And again, A and B is the same as B and A, right? And so B given A is A and B divided by A. Okay. We found the probability of defaulting given that they were married was the probability of defaulting and married divided by the probability that they were married, right? Because married is the given probability. Which we know, right, either from these probabilities or just from before, right? We're doing the same thing over and over again, right? And so the probability of D and M, or M and D probably, was 79 over 300. Over the probability of M, the probability of M is 143 over 300. Remember, when you've got a fraction over a fraction, you have to flip the denominator and multiply, which is what lets us cancel that 300. So that becomes 79 over 300 times 300 over 143. I'm going to show these canceling here. putting me at 79 over 143. And just to keep it on the same page, I'm just going to do that in Desmos here. 79 divided by 143 is 0.55244755524. I'll do 0.5524 is 0.5524, which is exactly what we found before, right? So it doesn't matter if you use the formulas or if you can just reason your way to it. I actually find that the formulas are a little bit more structured. It helps me out. But if you don't find that, then that's okay. You don't have to use them. You can answer the questions however you'd like. Okay. So if we compare 55% versus 26%, right? Married people and single people who default on their loans, right? And I've got it here, I guess. The chance that a customer will default if the customer is single is 26.11%. And that's substantially less than the chance of the default if the customer is married, which we found was 55.24. Given this information, right, do we suspect that there is a dependency here? Yes, we do. Right, because these probabilities are not similar in any way, this just confirms that there is a dependency here. So I'm going to bring this down so we can just talk about it a little bit more. Oops, paste image. This discrepancy in probabilities confirms our suspicions. How do you spell suspicions? I'll just go with that. Suspicion. No. Just do that. So this discrepancy in probabilities confirms our suspicions that whether a customer defaults is conditional, underline is conditional on marital status. Okay. Which leads us to the idea of independent events. So independent events would be if there was no difference in the probability of defaulting if you're married or if you're single, right? Then that can happen. But then we would expect those probabilities overall to match just the probability of defaulting, right? Come on. Okay. So the probability of defaulting overall, we found was, or we said was, the probability of D was 120 over 300, which I can confirm just to show you, but 120 over 300 is 0.4. Okay. So that's where they get this 0.4 from. Okay, so the probability of defaulting overall is 0.4. So what we would expect within each category is if it didn't matter, right? So here, if marital status had no effect on defaulting, oops, we would expect the probability of defaulting, given that they were M, would be roughly the same as the probability of defaulting given that they were single, which should be roughly the same. And we do allow some wiggle room, right? Just because of small sample sizes and just, you know, how surveys work. But it should be roughly the same as just the probability of defaulting, right? So what we would be saying then is that they would be independent. What we've seen is that that's not the case here, right? And so the probability of D given M, so defaulting given that they were married, was 55%, and probability of defaulting given that they were single is 26%, okay? And so the reason we're able to say that they are D and M are dependent is because the probability that the probability of D given M is not the same as 0.4, right? The probability of defaulting, right? And therefore it's not the same for the singles either, right? And so if they were roughly the same, then we could say that the events are independent, right? So had no effect, and we would say M, S, and D are independent. Okay. So two events A and B are independent if the probability of A given B is just the probability of A, right? If A doesn't depend on B, then the probability of A given B is just the probability of A. Same thing, again, the second one is redundant, we don't need it, is the probability of B given A should just be the probability of B if they're independent. Okay? Otherwise, the events are dependent. Okay? So the multiplication law, let me see here, see if I can grab this whole thing here. Uh-oh, might not fit. Ah. Okay, that's okay. I'm gonna crop this up here, crop top it. There. And I'll do the same thing here. Took way too long, but there we go. Okay. So what we're going to look at is the multiplication law, which might sound familiar because if you want to know, so if you're interested in the probability of A and B, so you don't have the probability of A and B, but you do have the conditional probability and maybe the probability of B, then this is the best way to find the intersection, the probability of the intersection A and B, which is just going to be the probability of A and B is going to be the probability of B times the probability of A given B. Now notice here that I didn't mean to go, I want to go, just go here. The probability of A given B from before, right, is the probability of A and B divided by the probability of B. So now if we solve for the probability of A and B, then all we need to do is multiply both sides by the probability of B. So then this would have to go over here, and I would have the probability of A given B times the probability of B is the probability of A and B. Usually to write things a little bit nicer, I switch things around, but I just wanted to show you where it came from. And then if we just kind of around the equal sign, do a little switcheroo here, then we have the probability of A given B times the probability of B. Notice that we've rewritten probability of B times the probability of A given B. But just remember, if you have 4 times 3, that's the same as 3 times 4, right? And so it doesn't matter, multiplication. Okay. And so we've just rearranged that one formula to solve for the probability of A and B, if that's something that we're looking for. Okay. And so what we can do is we can look at, so let's say we wanted to know the probability of defaulting, the probability of defaulting and being married. Let's assume that we don't have the entire table, but we do have the probability that someone's married, and we do have the probability of defaulting given that they were married. So from there, we can just rework the equation and find 26.33, which should be the same as that initial probability that we found, right? I think it was, where did we have it? Married and defaulting was 79/300, so it should match that. Okay. Go back here. Whoa. Or 79/300 from the table. Let's do 79/300. 0.2633333. Roughly the same, right? But that's assuming that you don't have the body of the table, right? The individual counts. Okay. So the multiplication law is useful when we know conditional probabilities, but do not know the joint probabilities. Okay. What if we think about the special case where A and B are independent, right? So if we think about here, the general case is that the probability of A and B is the probability of B times the probability of A given B. Okay, so let's jot that down. The probability of A and B is the probability of B times the probability of A given B. Okay. One thing to remember is that if A and B are independent, right, and that's a big if, right, then the probability of A given B is what? It's just the probability of A. Okay, so that's what leads us to the multiplication law for independent events, is that the probability of A and B is the probability of A times the probability of B. right? Because here we've got the probability of B, and then what we end up with, if A and B are independent, then we just multiply by the probability of A. So then we have the probability of B times the probability of A. If A and B are independent. Otherwise, you're going to need to rely on those conditional probabilities. Okay. Oh yeah, that's just a summary of that. So the extension of that is going to be what we call Bayes' theorem. Now, Bayes' theorem looks complicated, but it's actually not. It has to do with conditional probabilities. So let's bring it in and see what happens. So Bayes' theorem, oh, okay, I guess that works. Bayes' theorem is kind of the basis of what we call Bayesian statistics. And it's this idea that we don't just collect data and then we figure out what's going on based off of that data. Instead, we have some idea of what we expect is going on. And then we kind of update it with information that we get from data. Right, so we do rely on data, but in kind of a different way, where we establish some understanding, some idea, and then based off of what's actually happening, it kind of corrects itself. Okay, and so what we're going to have is we're going to talk about prior probability. So that's kind of our initial outlook. If we think back to the defaulting on the mortgage example, well, the prior probability would be, well, the probability that someone defaults was 0.4 or 40%. So that's what we would expect across both categories, right? But then we saw information that made us adjust that, okay? So the prior probability is just kind of our initial starting point. Okay, and then what we do from sources like survey data or product tests or however you collect information, we obtain additional information about the events. So given this new information, we update the prior probability values by calculating revised probabilities referred to as posterior probabilities. And so Bayes' theorem gives us a way that we can calculate these probability calculations. Now, I'm going to show you that it's the exact same as what we were doing, even though this looks really terrible, right? I'm going to break it down and show you that it's not so bad, okay? So for the case in which there are only two events, A1 or A2, they defaulted or they didn't default, they're married or they're single, right? So we're talking about two events. Bayes' theorem can be written as follows. Again, the second one is sort of redundant because you could just replace A1 with A2 up here and it would be the same, and vice versa. But what I want to do is I want to focus on just this one here. So I'm going to blow it up. I'm going to copy it and blow it up. Okay. If we talk about the probability of A1 times the probability of B given A1, so A1 happened, what's the probability that B is going to happen? So here, this is the same as the probability of A1 and B, right? If we set out the branch for these two cases where B is a follow-up event, Okay. Then the branch here, the tree diagram would look something like this. So either A1 happened or A2 happened. Oops. Then after A1 happened, either B happened or B did not happen. If A2 happened, B happened or maybe it didn't happen. Okay. And so we've got two initial possible outcomes, and then either B happened or it didn't happen. So it doesn't matter what's going on here, but if I want to find the probability of A1 given B, just using that previous calculation, right, what would I be doing? I would take A1 and B, right, the probability of A1 and B, and then I would divide it by the probability of B. But what I want to show you is that is this denominator here, right? This is the probability of B. Okay. So if A1 has some probability, right, then there's some probability of A1, and there will be some probability of A2 happening. Okay. Then B is conditional on A1 or A2, whichever one happened. And so the probability that we have on this branch down here is going to be the probability of B given that A1 happened. Okay. So the probability of B given A1. Same thing here, the probability of B not given that A1 happened, or the complement of B if you prefer. Next branch is going to be the probability of B given that A2 happened. And finally, we have the probability of the complement of B given that A2 happened. Okay. So if I wanted to know the probability of B happening, just kind of think back to when you were doing conditional probabilities. It might have been fairly recently, right? If you're in Stat 230 with me, but then you're on top of your conditional game, right? And so the probability of B happening is going to be, well, B happens, maybe I'll highlight here. B happens down this branch, right? But B also happens down this other branch. Okay, so B happens at the end of each of these branches. So the probability of A1 and B is going to be the probability of A1 times the probability of B given A1. Okay. So B happened and B or B happened here. Yeah. So the probability of B is going to be one of these, right? If it happened with A1, great, or it could happen with A2. As soon as you're saying or, we're adding, right? So we're adding these probabilities. And maybe I should add here, B1 happened after A1 or B happened after A2. Okay. So at the end of these, we have the probability of A1 and B is the probability of A1 times the probability of B given A1. Okay. Versus the probability of A2 and B is the probability of A2 happening times the probability of B given A2. Okay. Either of these give us a B outcome, right? And so what we say is, since these two since these two combinations are the only way B can happen, we see that the probability of B, and I'm going to cheat here a little bit, is going to be this probability, copy, is, hey, came up all weird, there, is going to be the probability of A1 and B, and maybe I'll delete this here. Plus this one. Okay. But notice that that's the same thing, and I'm going to zoom out here so we can have them on the same, or maybe I'll tilt my screen instead. Then we can really see it. How about that? Wow. Okay, so now we can compare, right, the probability of A1 times the probability of B given A1, well, that's this chunk here, plus the probability of A2 times the probability of B given A2. And so now we could just rewrite this as the probability of B, right? And so we know this formula, even though it looks scary, we already know how to deal with it, and we have already used it, right? If we've worked with tree diagrams before. Okay. And so usually if you've worked with conditional probabilities, you've already used Bayes' theorem, but you probably didn't call it that at the time because we oversimplified things. Technically, this is what's going on, right? And so of course you could do the same thing, but now with A2, right? Notice if you kind of pick it apart here, this is really the probability of A2 and B, right? Over, again, the probability of B happening, right? Because it's given B. So you could do the same thing with this other branch. Okay. Okay. Good. So let's do, I think there's an example here. Okay. Okay. Tempted to skip it, but it will be good to do an example. So all right, I give up. So we're going to consider a manufacturing firm, and maybe what I'll do is I'll crop this so we can have it big sized there and here. How about that? So just to see it in action, okay, if we are talking about a manufacturing firm that receives shipments of parts from two different suppliers, right? So two possible outcomes, supplier one or supplier two, right? So that's the scenario that we just saw. Then we're going to let A1 denote the event that the part is from supplier one, and A2 denote the event that the part is from supplier two. Currently, 65% of the parts purchased by the company are from supplier one, right? So more than half are from supplier one, and the remaining 35% are from supplier two. So if a part is selected at random, right, then we would assume that 65% are from supplier one and 35% are from supplier two. So now the quality of the purchased parts varies according to their source. Historical data suggests that the quality ratings of the two suppliers are shown in table 4.7. 6, which I didn't include because it's summarized down here. So I didn't include that. But that's okay, you don't need it. So if we let G be the event that a part is good, and we let B be the event that a part is bad, you could use the complement of G if you wanted to, right? Like we did up above, we used B and not B. Okay. Then we can find these conditional probabilities. And so this would be given to you, right? The probability that the part is good, given that it came from supplier 1, is 98% or 0.98. The probability that it's bad, then, given that it came from supplier 1, has to be 1 minus 0.98, right? Has to add up to 1. It's either good or bad, nothing in between. Same thing here. If it came from supplier 2, the probability that it's good then is 95% versus the probability that it's bad is 5%, so a little bit higher. So now suppose that the parts from the 2 suppliers are used in the firm's manufacturing process and that a machine breaks down while attempting the process using a bad part. Given the information that the part is bad, so now we know that this part is bad. What's the probability that it came from supplier 1? And what's the probability that it came from supplier 2? Remember, we went into this thinking 65% of our parts came from supplier 1 and 35% of our parts came from supplier 2. But now that we know that this part is bad, is that going to change our probabilities? Probably, right? So what we can do is we can set up a tree diagram. That's probably the easiest thing to do. So it's in the notes, but I'm going to recreate it here because I find that it's easier if we just kind of talk about it. So first thing we do is we set up our branches. I'm going to give myself quite a bit of space here. So it's either from supplier 1 or supplier 2. I'm going to highlight here that this is kind of our supplier layer, right? First, it comes from either supplier 1 or supplier 2, and they've already given us the notation to use, and so that's what I'm using. We were given that the probability of A1 was 0.65 and the probability of A2 was 0.35. Okay, so far so good. Then whether the part is good or bad, well, that can happen from either of these suppliers, right? So good or bad. What we know is the probability that it was good, given that it came from A1, is 0.98. Whereas the probability that the part was bad, given that it came from A1, was 0.02. Okay. Again, the probability that the part was good, given that it came from A2, was 0.95. Oops. And the probability that it was bad, given that it came from A2 or supplier 2, was 0.05. What I like to do and what I find is helpful, but it's not proper, but I find it helpful, is at the end of each branch, I like to write the combination of things that happened at the end of each branch. That's just to help me see what, kind of a shorthand version of what happened. So here A1G happened, here A1B happened. Oh. A1B happened. Next one, oops, A2G happened, and then A2B happened. That's just shorthand for A1 and G, A1 and B, right? But it just helps me to see what's going on. Okay, so if we know that the part is bad, then what's the probability that it came from supplier 1? Okay, if you had to figure this out just by given this information, what would you do? Well, you would have to find the probability that it was bad and came from supplier 1, right? So here we could say that the probability of A1 and bad, well, we could multiply down the branch, 0.65 times 0.02. 0.65 times 0.02. I usually don't use the multiplier here. Maybe I should write it in brackets. It's a little bit more adulty. Like that. Okay. So 0.65 times 0.02. I'm going to grab my calculator here. Who knows? 0.65 times 0.02 puts me at 0.013. Okay. Typically what I do is I find the probabilities at the end of each of these, because that saves me time later on. Then I don't need to think about, oh, which one do I have to calculate next? If I've just done them all, then that's good, right? So here, I'm just going to go ahead and maybe not. To save us some time, I'm not going to, but I would just go through, and just like I use shorthand here, I'm cheating, right? A1G, then I would just jot down what 0.65 times 0.98 is when I multiply it, right? And so then I would have the probabilities. I haven't written them out properly, but I would have them and I could use them. So another way that we could end up with a bad part is if we picked an one from supplier 2, right? And so the probability of A2 and B is the probability of A2 times the probability of B given A2, which is 0.35 times 0.05. 0.35 times 0.05 is 0.0175. Okay. So then what we could do is we know now that the probability of being bad, right, the only options here, and notice that once you have all these probabilities at the end here, so we'd have to calculate A1G and A2G as well, you could add those up and make sure they add to 1. Right? But I'm skipping that step right now. So the probability of B happening, well, B can happen, B happens down this branch, or B happens down this branch, right? As soon as I'm saying or, I need to multiply it. So the probability of B overall is 0.013 plus 0.0175. Which is 0.0305. Okay. So now I can find the probability of, now we can find the probability that the part came from A1, supplier 1, given that it was bad. Well, that's the probability that it came from A1 and it was bad, divided by the probability that it was bad. I have both of those probabilities, right? I have the probability that A1 and bad, so 0.013, and I have the total probability of 0.0305. So now I know that this probability is going to be 0.013 divided by 0.0305. If it turns out to be a nice number, that's great. If not, I usually just keep it kind of sloppy, but here we go. I'll do approximately equals because I'm going to be rounding at some point here, 0.4262. I'll keep 4 decimal places. And if I scoot this over, I can do the same thing. The probability that it came from supplier 2, given that it was bad, is the probability that it came from supplier 2 and it was bad divided by the probability of it being bad. We have all that information already. 0.0175 divided by 0.0305. 0.0175 divided by 0.0305. 0.0175 divided by 0.0305. Again, I'll round to 4 decimal places, 0.5738. Yeah. These probabilities are slightly different, right? If we compare it to the probability that it came from supplier 1, right, versus, so here I want to say versus, the probability that it came from supplier 1 was 0.65, and the probability that it came from supplier 2 was 0.35. Right, so notice now that this conditional probability, if I know that the part was bad, then the probability that it came from supplier 2 is quite a bit higher, right? It's more than half that it would be from supplier 2. So they go through and do the same calculation, but I find that it's helpful if we work through it together. So that's what I did. And right. So here again, we said, okay, well, we started with 0.65 from supplier 1, and then knowing that it was bad, the probability that it came from supplier 1, it dropped to 42.62, right? And so if the part is bad, the chance is better than 50-50 that it came from supplier 2, right? So that's not good. You know? We can extend Bayes' theorem to any number of events, right? We focused on, okay, supplier 1, supplier 2. We could extend it to technically an infinite number of suppliers, if you want to think of it that way. But usually it's, finite. As long as all the sets make up all the possible outcomes or events, copy, then we can use Bayes' theorem. So Bayes' theorem is applicable when events for which we want to compute posterior probabilities are mutually exclusive. Meaning what? Mutually exclusive, remember, means that they can never happen at the same time, so there's no overlap. And their union is the entire sample space, right? So this here means that we the events I'm drawing a blank. What do I want to, I'm this close to what I want to say. The events, and I'm trying to not say make up the entire sample space. All possible events are accounted for. That's what we'll say. All possible events are accounted for. Okay, so that's what that says. And here, mutually exclusive, I'll just remind you, come on. No two events can happen at the same time. Okay. For the case of n mutually exclusive events, so now we have A1, A2, A3, AN, right, all the way up to AN, meaning we could have n suppliers, right? We're not restricted to 2. It's just even making a tree diagram with n equals 3, right? 1, 2, 3 suppliers. Well, it gets kind of weird, right? Because then each of those 3 branches have 2 possible outcomes, good or bad, right? And so our tree gets huge really quickly, right? And so, but we can still use Bayes' theorem. We don't need to map it out with a tree anymore if we have a good grasp on Bayes' theorem. So, so then A1, A2, A blah, 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 all the way up to AN has to make up all the possible events, right? And so whose union is the entire sample space. Bayes' theorem can be used to compute any posterior probability. The probability of AI, so I is just a placeholder for A1 or A2 or A3 or A4, given B, okay? If we break this down, the probability of any AI, right, I is just a placeholder, given B is going to be the probability of AI, right? I could be 1, could be 2, could be 3, doesn't matter. As long as you're consistent, right? So if we think that I is 3 in this case, then the probability of A3 given B is going to be what? It's going to be the probability of A3 and B, which is the probability of A3 times the probability of B given A3, right? That's fine. So here, this is the probability of A1 or AI and B. And again, if we have A1, A2, A3, A4, A5, all the way up to AN possible events, then we need to think about B happening for every single one of those streams, right? And so here, this is how we would calculate and extend the probability of B for more than 2 outcomes. So here, this is really, you can think of it as the probability of B. So you can handle that, right? It's not as complicated as it looks. It becomes complicated because we've got those conditional formulas and we've got little subscripts and fun stuff like that. But overall, you have used it before, just maybe not in this way. I see that I am very nearly out of time. So what I'm going to do then is the recording that I'll post is going to cover the rest of these chapter 4 notes. So it's going to go through random variables and probability distributions, both for discrete random variables and then for continuous random variables. It's just catching up here, all of which is likely review from statistics, right? Or we'll cover it in more detail in Stat 230. Okay. If you have any questions, let me know. I'll stop this recording, but otherwise, have a good long weekend, and I'll see you next week.